Hi, we're now starting the third big chunk of material for this module on matrix methods. How to solve matrix problems like inversion or eigenvalue problems for very big matrices. Okay, so we're now on to matrix problems. And I hope you've been following through on the lecture notes, on everything. This is now chapter 4. As I say, people ask what's going to be on the exam. Look at the lecture notes. They are really the expansion of the syllabus for this module. And let's just talk very generally now about two key types of problems that we're interested in. So first one is, for want of a better word, inversion. Sometimes that's and that's where you have a AX equals B problem, but where A is very large. So you know how to do a 3x3 inversion, pretty much. May have to look it up if you haven't done it for a while. Certainly know how to do a 2x2. That was probably ingrained in you from sort of A-level times. But if you had a 100 by 100 matrix or even larger, it becomes really impossible to do by hand, and you need some sort of iterative method to find it. And it turns out that a big class of practical problem in numerics, like say the boundary value problem that we encountered just in the last video, involves a very big matrix that we need to invert. So now in MATLAB you can there is a routine A/B that does it for you, but the aim of this module, this part of the module, is to actually understand how these inversion routines would work and how we assess whether they are stable, they will converge or not. So that's the first type, which is inversion. The second type is eigenvalues. And this is where you have a matrix times a vector vi equals lambda I vi. So vi are eigenvectors, lambda I are eigenvalues. Okay, so it's a special vector that you plug into A, if you like, where it keeps its same direction but just multiplies its length. And they're called eigenvectors. And it turns out that a whole bunch of other problems can be expressed as eigenvalue problems. And the one you probably come across every day is the Google search engine. Let's just put it up there. Say a little bit more. So the Google search engine ranks web pages, right? So whether you're searching for coffee, Lego, guitars, whatever, you want them ranked in order of popularity. And I don't know if you've ever wondered how it does that ranks. Well, at its heart is at its heart of the Google search engine is an eigenvalue problem. So all the information is contained within the matrix, a Google matrix, and you find its eigenvalues. Now, if you want to, there's more to this, obviously, but if you look up on Google, PageRank, that's the name of the algorithm that Page, who was one of the founders of Google, came up with. And there's if you also look up mathematics of PageRank or something, there's a really nice article out there where it goes into all the details, and there's some more advanced maths like graph theory and things like this that you can do in year 3. But at its heart, there's this something called at its center is the what's called the power method for finding eigenvalues. And this is a way of finding eigenvalues of a very large matrix. And we're going to be covering an elementary form of the power method in this module. So it's not going to give you the whole Google search engine, but aspects of the Google search engine will come into this module. So that's very interesting, isn't it? That actually every day I mean, there are other search engines, but let's face it, this has dominated the market now. And every time we punch into that little white box, it's actually doing some sort of eigenvalue to reorder the websites for you. So that's a real sort of current application. There are more in the area of matrix inversions, but in the interest of time, I'm just going to move on. And if you look back right at the initial lectures videos, 1A and 1B, you'll see more examples there of these sort of matrix problems. Okay, so what we want to encounter then is an introductory course on matrix methods for really big matrices, not for small matrices anymore, is something that tells us about matrix inversion, and that's what we're going to do. So we're going to look at matrix inversion, probably in more detail than, and then we're going to look at eigenvalues. So matrix inversion is going to center around two methods called Jacobi and Gauss-Seidel, and we're going to look at issues to do with convergence of these methods and how we assess convergence of matrix inversion methods, and then we're also going to look at the power method, and that takes us through the new part. So that's some motivation for why we bother doing matrix methods. Basically, they kind of form the core of a lot of the algorithms you use, even if they haven't got matrix method on the label. Underneath, you'll find some sort of matrix method. So they're incredibly important, and that's where we're covering them. So in the lecture notes, I revised simultaneous equations. I don't want to go into that again. That's kind of year 1 material. But what I want to do is revisit something from the first year, which is called Gaussian elimination. And there's a good reason why I want to do this. Because we're going to see this through as an approach to the inversion problem now. X problem. So this is the first topic, if you like. So one approach to the inversion problem is to decompose A into separate parts. And that, in fact, we're going to look at a specific type of decomposition, which is two special matrices, which I'll describe as we go on, which involves breaking them into two. So A may be difficult to invert, but if we break it into a multiplication of two matrices that are easier to invert, notably Al and U, they have special structure, more as we go on, then we can solve. That's a way of solving big matrix problems. And it turns out your Gaussian elimination, which you did last year, is actually a form of decomposition. So that's what I want to show you. That's why I want to go through it again, because I want to show you. So we're going to go through Gaussian elimination, but we're going to keep very close attention as we go through to the sort of coefficients that we use, the operations we do, and we're going to then be able to reinterpret. So another way of looking at it is we're reinterpreting an existing method from the past. Okay, so this is what we're going to do now. So we're going to solve this problem. It's going to be a 4x4 matrix, and this is the one in the lecture notes. 2, 3. And this is useful going through all the steps rather than just showing it up on slides where I could whisk through it. I really want us to sort of focus on how this, even if you were really a pro at doing Gaussian elimination last year, we want to really sort of pay attention. So this is shorthand. That's your B vector. So we're solving A, x equals B for x. Yeah. And then this is your matrix A. And of course, with the idea of Gaussian elimination is that we identify things called pivots, and we clear the column below each pivot. So normally the pivot is a diagonal. And clear the column below by doing row additions, multiplications, or subtractions. Yeah. So we just so in this first example, we want to clear. This is going to be our pivot. That's going to be in the square box, and we want to clear everything below this column. So in this column below this pivot, and we're gonna use some dimension curve. We're going to identify the row. See, these are rows. I'm going to call this row 1, row 2, row 3, row 4, the fourth row. So to clear under the pivot, we do these operations. I'm just going to write them up in the first one. So first of all, we do row. So we leave the pivot row alone, yeah, and we just then operate on it, if you like, with row 2. So we do row 2 minus 2 row 1, yeah, and that will give us 0 in that first element below 1. And then we'll do row 3 plus row 1 and row 4 minus 3 row 1. Okay, so that should be familiar from previous years. It's just your simultaneous equations. We're just identifying a pivot row that we leave alone, and then we clear below it with these operations. But what I want you to take a note of now is, as we're doing that, is what the coefficients we were using to perform that clearance. So we've got a -2 here, a +1, and -1. So I'm actually going to just write those operations on a fresh slide, okay? So we keep contacting it. So we're going to we had row 2 minus 2 row 1, row 3 plus row 1, row 4 minus 3 row 1. But what I'm going to do underneath it, I'm going to write a number, okay, these coefficients, and I'm going to put the coefficients in what I'm going to call a matrix of multipliers, because all these things are multipliers, right? -2. But the other little alteration, which will come up apparent why I need to do it, is I'm going to, but also I'm going to apply a -1 multiplication as well. So I've got these coefficients, -2, +1, -3. They're going to go into a matrix, and I'm going to call it M, and the elements of M that are going to correspond to the row indices here. So it's going to be M21 equals 2. And this is where I mean the -2 multiplication. I've taken the -2 and multiplied by 2. Just something you have to remember. Then you can have M31 equals -1. M41 equals 3, plus 3. So what we're doing is filling a matrix. This is going to be the matrix M, which we're going to actually call something else in a minute. Let's call it M for the time being. And well, we haven't filled in the diagonal, but we've got M21. We're filling in basically this first column in this matrix. So M is a 4 by 4 matrix. You have 2, -1, 3. So we're doing Gauss elimination, but we're just keeping track of the coefficients, and it will turn out that this M has special structure, and it corresponds to a matrix decomposition. Okay. So so as we go through the Gaussian elimination, we're gonna apply that. Okay. That's the key idea. So M, just looking ahead, I'll tell you that will form part of a matrix decomposition of A. Which is good. Which maybe makes sense, because if you might be able to interpret all these row operations basically as some big matrix operation applying on the rows, yeah. And these are coefficients. So that's maybe a more compact way of thinking of it, of your old friend. What I'm going to do is I'm going to actually just show I'm just going to give the operations for 2 steps now, and then show the results. So we do. Let's do it before we do what we did before. Row 2, row 1, which means M21 is 2. R3 plus R1, which means M31 is -1, and R4 -3R1 is M41 equals 3. Then we want to clear for the next pivot, which is the next element down in the diagonal. So we have 1 in the first corner. Now we clear the column below, the 2 elements below the column. We then have R3 minus 2R2. So M32 equals 2. And you've seen the pattern here. The matrix elements indexes correspond to the first row's index 3, second row's index 2, and it's minus the coefficient. That's kind of the rules. And then we have R4 plus 2R2 gives M42. Don't forget we're using row column index here. So M is 4th row, 2nd column is -2. Again, should be revision that from last year. So then you end up with this matrix. So we cleared the first 2 columns. We have 0, 0, 0, 1, 0, 0, -1, -2, 2, 3, -2, 1. And of course, don't forget, we also operate on this final column as well. So these change. Okay, so Gauss elimination. So we've cleared that under that pivot. We've cleared under that pivot. We've just got one more pivot to clear, and that's under the -2. So finally, we have R4 plus R3. So we add row 4 to row 2 to clear that element there. So that corresponds to M4, first element 4, 3 equals -1. Yep, take the minus sign again. And we finally then have it all cleared nicely. And we end up with the last row. Which is 10, 11, minus 14, minus 4. Apologies, gremlins in the work. Okay, and just before I stop, I just want to make some observation here. We've gone through our Gaussian elimination. We've got all these zeros here, but we've ended up with, actually we ended up with a matrix which has a special form, and we're going to call that U. And the name for it is upper triangular. Yep, the whole reason we'll get onto a bit more next time. But what I wanted to show you is just we've gone back through Gaussian elimination. We've picked out that all the coefficients we've been multiplying through are going to be brought into a matrix. And then we've also observed when we finish Gaussian elimination, we end up with a matrix that has a special shape. It's triangular, which is very useful because it's just got a single element in the corner, and it's upper triangular in this case. Okay, so I'll continue on with this next time. See you next time.